Welcome back to Mass Transfer Operations 2 course, and now we will be discussing on membrane separation technology. The syllabus is as follows. First, I will be discussing on fundamentals of membrane separation processes, then we will be discussing on manufacturing of membranes, advantages of membrane separation processes, limitations of the membrane separation processes, and approaches to improve the membrane performance. The third topic is the various models and application in design aspect. Then we will be discussing on electric field enhanced membrane separation processes. Finally, we will be discussing on micellar enhanced ultrafiltration, that is MEUF. So, we will be discussing the fundamentals of the membrane separation processes, how this membrane separation process is different from other separation processes. We need to understand first. Suppose the schematic of the any separation process is like that, say this is the suppose separation process, then we will supply feed and energy or matter actually is required to separate something from the feed, and then we will be getting the product stream. So, this product stream may be of, say we can say permeate, may be of retentate in case of the membrane separation processes. So, first of all we need to understand the definition of membrane, that is, say we can say it is a phase separating two streams, feed and product, that allows preferential transport of a species through it. So, it can be regarded as the, we can say, the semi permeable barrier, or it will allow one particular component to be retained and the other component to be permeating through this barrier. Okay. So, this barrier may be solid, may be liquid. Okay. And for that we need the this relevant driving force, as we can say pressure gradient, maybe temperature gradient, maybe concentration gradient, or maybe electropotential gradient. Okay. The common materials for the membranes are like polymeric, then liquid emulsion, and then inorganic, say we can say ceramic and metallic membranes. Okay. So, we will be classifying the membrane in the beginning. Actually this means one major part is polymeric membrane, then we have liquid membrane, and the third category is inorganic membrane. So, in polymeric membrane, say we have two different types of membranes, like one is this dense membrane and another is porous membrane. Okay. In case of the dense membrane, we can say this maybe it is isotropic or symmetric, or maybe asymmetric also, and another type of dense membrane, that is composite membrane. Okay. In case of the porous membrane, that may be isotropic or may be microporous. In most of the cases, we can say whenever we will be discussing details about the membrane separation processes, we will find that, say in dense membrane systems we have, say reverse osmosis membrane, then nanofiltration membranes, and most of the industrially available membranes are asymmetric type, that is we can say we will be discussing details later on. And but whenever we will be talking about, say microfiltration membrane or nano ultrafiltration membranes, these are regarded as the porous polymeric membranes. And the another type of membrane, that is liquid membrane, these are of three types. Say one is this emulsion liquid membrane, say we can say this one ELM, and another is supported liquid membrane, say SLM, or we can say this one immobilized liquid membrane ILM, and the third one is this bulk liquid membrane. Okay. So, these three different types of liquid membranes are available, but most of the liquid membranes are not used industrially. This is, we can say in the form of this, we can lab scale studies. And the third type of membrane, that is we can say this one inorganic membrane. There we have ceramic membrane as well as the metallic membrane. Out of the ceramic and metallic membrane, ceramic membrane is widely used for so many applications, and the ceramic membrane has the advantages over the other two types of, we can say, membranes like polymeric membranes and liquid membranes. We will be discussing also in detail after that. So, this whenever we will be talking about the separation processes, we have these two different types of separation processes. One is this equilibrium separation process and another is the rate governed separation processes. So, whenever we will be discussing about the equilibrium separation processes, that product species distribution are in equilibrium and degree of separation is controlled by the equilibrium. When a system reaches its equilibrium, then the separation process stops, and as we know that as per the Chatellier's principle, if we want to get this reaction to be in the forward direction, then we need to take out the product from the product side, and then only we can say this equilibrium will be shifted towards the right hand side, and then we can say the process will be in the non equilibrium condition, then we will get the desired separation or we can get the separation. So many examples are there in case of this equilibrium separation processes, like say distillation, then adsorption, absorption, say ion exchange, and so many crystallization. So many processes are there which are the separation is governed by the equilibrium. And the another category of the separation process, that is we can say rate governed separation process, that composition of the product and extent of separation are governed by the physical transport of the species through the interface. Whatever the interface actually we are discussing here, that is nothing but the membrane. So, that we can say the semi permeable barrier, we talk this one as the semi permeable barrier, because it allows one component to be pass through this barrier and restricting the one component this one through that. Okay. The examples are like reverse osmosis, ultrafiltration, nanofiltration, then microfiltration, etc. Recovery of non volatile solutes, then we can say usually from these aqueous solutions in hydrometallurgy. In so many these one places we will be discussing the application of membrane separation process in so many industries and so many places. So, there whenever we will be talking about the membrane based separation processes, we will find that the separation, or we can say this one extent of separation, these will be controlled by, we can say either this pressure gradient or concentration gradient or electrochemical potential gradient, and the size of this molecule to be separated by this semi permeable barrier. Okay. Now, we will be discussing about the details of the polymeric membranes, say maybe isotropic, symmetric or homogeneous, whatever we say this one. So, pore size distribution is same over this whole matrix. So, there is no base, whatever the matrix is there, that is we can say pore size distribution is same, but you see in reality the getting symmetric or isotropic or homogeneous membrane is very tough. So, generally we get other membranes which are not isotropic or not symmetric or not homogeneous. Okay. Like asymmetric membrane, that thin porous skin that does not have a mechanical strength is placed on a porous base like this, the skin acts like the membrane. Okay, base does not offer any resistance. So, base actually is highly porous, like this. If we say this is the base, and then over this one skin actually is placed here. Then whenever this material actually will pass through this one, only the resistance will be offered by this membrane material, not this we can support. Okay. Support is highly porous. In general, these are in the say micron, or we can say this one in the millimeter. Pore size of the base is in sometimes in the millimeter range also. Then composite membrane, that is we can say this one a layer of this thin film over polysulfone or PTFE film is coated. So, we can say this in composite membrane, sometimes we have 2-3 layers of the polymeric films, then it forms this composite, but in most of the cases we will be getting the asymmetric membrane, because you see this one whenever we will be placing the few layers one after another, then the pore size distribution and porosity will not remain uniform. Okay. And the one advantage of using this composite membrane is that it is highly stable in any harsh pH condition. And another type of membrane, that is we can say this electrically charged membrane. So, an electrically charged membrane material has ionic groups that give the membrane fixed charge sides. So, like tetrafluorosulfonic acid isomer naphthalene has SO3 minus group on the PTFE base. So, whenever we have electrically charged membrane, then we will be able to separate this charged particle, we can say this one with the high selectivity. Okay. So, in case of this inorganic membranes, so we have these two different types of membrane, one is the ceramic membrane, another is the metallic membranes. In case of the ceramic membranes, technique of making a ceramic membrane in sol gel technique like this alumina and zirconia membranes are more common. Alumina alkoxide is hydrolyzed at controlled temperature and pH to a stable colloidal solution. A binder like PVA is added to the sol in a small quantity, then a suitable porous ceramic substrate is coated with the sol when this one gets converted into a gel by losing water. The coated substrate is dried under controlled condition and then slowly heated to and sintered at around 100 degrees Celsius. Like as in asymmetric ceramic membranes, thin porous skin that does not have a mechanical strength is placed on a porous base. Skin acts as the membrane, base does not offer any resistance. Okay. We will be discussing also the detailed step by step procedure of the ceramic membrane fabrication as well as the polymeric membrane fabrication also. In metallic membrane, the palladium membrane in the form of a thin film or a filled in tube to separate say hydrogen this from the from a gas mixture, that is also available. Whenever we will be talking about the liquid membranes, we have these three different types of membranes. A liquid may act as a separation barrier between two phases when transported across by solution diffusion mechanism. We will be discussing in detail about the what is the solution diffusion mechanism. The appropriate technique has to be adopted to stabilize liquid membranes, so that it does not get ruptured during use. But you see this one I told earlier also that liquid membranes are not used widely in the industry due to their instability, but this is used in the lab scale especially where the solute concentration is very less. In case of this very dilute solutions, liquid membranes are effective, but that is in the lab scale only. So, there are three different types of say these three common types of these liquid membranes. One is this emulsified liquid membrane, another is we can say this one supported or immobilized liquid membranes, and third one is this bulk liquid membrane. Okay. Now, we will be discussing about the types of motion of the molecules through the membranes. One type of this one motion of the target component, or we can say this one molecules through the membrane is called permeation, that we say DDD mechanism. Okay. So, first D stands for the diffusion of the solutes in upstream phase of the barrier on the top layer of the membrane. Say if we say this is the membrane barrier, then one molecule actually will be transporting, then it will be diffusing from the bulk to the we can say membrane surface. Then the second step will be this diffusion of the solute particle through this the target component, or we can say this molecule through this one. So, first is D this one, then we can say this one diffusion through the membrane, and then third D is the dissolution in the say downstream, or we can say this one, this is say we can say this one permeate side, or this is the we can say this one permeation. Okay. Then another molecular movement is called this Knudsen diffusion. We know this one, then when mean free path of the gas molecule is greater than pore diameter, then forward movement is done by collision. Suppose we have one pore and one particular target component actually is moving, and this mean free path is greater than the diameter. Like this, whenever it will be moving to the next position, before that it will collide with this wall of this pore, then we can say this one, it will, then we can say this forward movement actually is controlled by this Knudsen diffusivity. This is, we can say this something different from the molecular diffusivity like this. So, in that case we can say this one, according to this Knudsen diffusivity, when dP by lambda is less than 0.2, or we can say this one pore diameter by mean free path, the ratio is less than 0.2, then we can say this one Knudsen diffusivity Kd is equal to 2/3 of this ut into Rp, where ut actually is the average velocity of the molecules, and say Rp is equal to, we can say, pore radius in centimeter or in any unit. Actually Rp means pore radius, means through which actually it is moving. So, this is say dP. So, dP pore radius is half of this dP, and say into 8 RT by pi into m to the power 0.5 into Rp. So, in general we can say this one Kd actually in centimeter square per second is 9700 into Rp into T by m to the power half, just by simplification we will be getting. So, where T is the temperature and m the molecular weight. Okay. So, this is, we can say this one, as per the Knudsen diffusivity, the movement of this target molecule through this porous membrane is controlled by Knudsen diffusivity. And then third type is convection, when these pores are larger diameter, than viscous flow through the pores is done by the convection. It is simply, we can say this one, whenever we will be increasing the pressure, then this target molecule will be passing through this one due to only simple convection. Okay. Now, we need to do the process categorization. So, as per the pressure driven processes, we have these 4 different types of membrane separation processes. One is the microfiltration membrane, then second one is this ultrafiltration membrane, third one is this nanofiltration membrane, fourth one is reverse osmosis membrane. And in terms of concentration driven processes, we have this dialysis, hemodialysis, electrodialysis, pervaporation and liquid membranes. We will be discussing briefly all these processes, because after that also whenever we will be discussing about the different models, there we will be discussing in detail, but in brief actually we will be discussing all these. So, like microfiltration membrane, pore size is greater than 1000 angstrom and operating pressure is in the low range, we can say this one 2 to 4 atmospheric pressure is required to to separate the solute particles, because in case of the microfiltration, the molecules with the molecular weight more than 1 lakh is separated by this microfiltration membrane, and as the pore sizes are large, that is why we can see this less amount of operating pressure is sufficient to pass the solvent through this. Then transport mechanism definitely will be convection only, as we are increasing the pressure, the solvent which will be passing, and then solutes with high molecular weight like we can say protein, pectic materials will be retained by the microfiltration membranes. There are so many applications, especially we can say this in case of this fruit juice clarification, like separation of very high molecular weight proteins, clays, pigments, then red blood cell, then clarification of fruit juice and cheese whey beverages, and so many applications are there for the microfiltration membrane. Then ultrafiltration membrane, the pore size ranges from 220 to 1000 angstrom. So, we can say this one, in case of the ultrafiltration membrane, the pore size is denser than microfiltration membrane. As the pore sizes are denser than microfiltration membrane, that is why the operating pressure range actually is to some extent higher than the microfiltration process. In that case, the operating pressure ranges from 5 to 8 atmosphere, and molecular weight of the solutes to be separated like 1000 to 1 lakh. Okay. Transport mechanism will be diffusion as well as this convection. When we have this high pore sizes like this towards this 1000, then this convection will be taking place, when the pore sizes will be around, say we can say around 20 angstrom, or we can say this one when the molecules of with molecular weight around 1000 or more, then we can say this one diffusion will take place. When the molecules with molecular weight in between, then these two will be controlling that, we can say diffusion as well as this convection will be controlling the transport mechanism. There are also so many applications, and we can say this one ultrafiltration has the maximum application in the industry. So, separation of high molecular weight protein, colloids, polymers, clarification of fruit juice, then paint recovery, latex recovery, then separation of oil, this one from oily wastewater, then water treatment, wastewater treatment, and so many. Okay. Now, we will be discussing about the nanofiltration membrane. Their pore size now become more denser, say only 10 to 20 angstrom pore size, means in the nanofiltration range, and then operating pressure is now higher than ultrafiltration membrane. So, that is why 10 to 25 atmospheric pressure require, or pressure gradient is required, and then partial separation of, we can say monovalent salts also are there, means for 65 to 80% monovalent salts are separated by nanofiltration membranes, and molecular weight of the solutes to be separated, that is in a narrow range, we can say this 200 to 800 molecular weight the solutes are separated. Mechanism will be permeation only. The applications are like dye removal, then recovery of whey protein, production of softened water for industrial use, then treatment of tanning effluent, textile effluent, and so many industrial this one wastewater treatments are available. But in terms of, we can see the operating pressure, as it is in a higher range, that is why we can say this one operating cost is to some extent higher than both microfiltration and ultrafiltration process. Now, the last process we say reverse osmosis process. This is also called hyperfiltration. Pore size is 2 to 10 angstrom, but we generally tell this is non-porous membrane, or we can say this one highly dense membrane. Then operating pressure is very high. So, we can say 25 to 40 atmosphere pressure is required for conducting this reverse osmosis process, and here we can say this one almost 95% of the NaCl is removed by reverse osmosis membrane, and transport mechanism will be like permeation, that is dissolution, diffusion, and desorption only. Okay, the applications are like production of potable water from sea water, especially in the Gulf countries where only this saline water is available. For the production of this drinking water, the reverse osmosis is used, and production of low salinity water for industrial use, then recovery of whey proteins, and so many other applications are there. In reverse osmosis, most of these solutes are retained, but due to this high operating pressure, the operating cost is to some extent high, and to this one withstand at this high operating pressure, the base material also this one should be very strong enough to withstand at that high pressure condition. Okay. Now, in case of this concentration driven processes, first process is, we can say this on dialysis. This is the oldest membrane separation process. Say, diffusion transport of one or more species through the membrane takes place like this. If we say this is the membrane, say dialysate actually is supplied here, and then say we can say this one solutes will be retained on the membrane, and then permeate actually will be coming out from the membrane. That permeate will be used for the, we can say for the patients like this. Whenever we will be talking about say dialysis of the kidney, then the permeate with the low salt content will be retained to this, we can say this patient. Okay, this and diffusional transport of one or more species through the membrane takes place, and pore diameter actually that is in the, we can say this in between, we can say reverse osmosis nanofiltration membranes like this. So, the pore diameter ranges from 0 to 10 nanometer like this up to 100 angstrom. The separation mechanism is like this: solution diffusion mechanism and difference in diffusivity of the larger and the smaller molecules, and thin dense film asymmetric membranes are used. Okay. The main application of this dialysis is that in case of this kidney dialysis, that is in the medical purpose, and other applications like this adjustment of the alcohol content in beer, removal of salt from these heat sensitive or mechanically labile compounds such as vaccines, then hormones and enzymes. Okay. Then the other process, that is we can say this concentration driven membrane separation process, that is hemodialysis. We know this one, the using this hemodialysis we can say the toxic low molecular weight compounds are removed from the blood using a membrane device known as this hemodialysis. So, the schematic of the hemodialysis is like this. This is similar to that of the we can say saline tube heat exchanger like this. Say from the cell side the dialysate actually is flown, and then dialysate will be out from the other part of the cell side, and this suppose this contaminated blood will be entering through this tube side, and then it will pass through this we can say this one through the tubes, and it will be dialyzed blood or purified blood actually will be coming out from the hemodialyzer. Okay, so, this schematic also of the hemodialysis for this purification of the blood is shown in this figure. Say from the patient, suppose the contaminated blood actually is taken, and then through this blood pump it enters into the hemodialyzer or say hemofilter, and then dialysate actually is entered from the we can say this one outside, and it enters into the hemodialyzer, and then using this ultra filtrate pump actually that what is called that the exhausted dialysate actually is thrown away, and the purified this one blood is we can say this one is again fed to this patient through this we can say this one booster pump. Okay. We will be discussing this one. So, this is we can say this one maintenance dialysis for patients suffering from kidney failure, and hemodialysis we can say this one as artificial kidney was first constructed by Kolf and Bark in 1945. And we need to remember here that in case of this hemodialysis, we need to make this isotonic solution, which is same osmotic pressure with the blood. Means whenever we will be putting this dialysate, that we need to say what is this we can say osmotic pressure, otherwise the blood will come into the dialysate, and then or the reverse may happen also, means a dialysate will enter into the blood and it will clot this blood, and then it will create the hazard to the patient. Then another concentration driven membrane separation process is called electrodialysis. So, say electrodialysis is a process of removal of the salts from an aqueous solution by transport through the electrically charged membrane. So, applied electrical potential provides the driving force here for the transport of the ions through the membrane, where E is equal to I square into Nr, where E is the electrical power consuming, and then I is the current, and then R is this we can resistance, and N is the number of charges. And E is about we can say this one 1.6 to 2.6 kilowatt hour per meter cube from a feed using 1500 to 2000 milligram per liter. The schematic actually of the electrodialysis is that say we have this so many say cathodes and anodes. These are say cathode, this is anode, say cathodes and anodes are placed we can say this one alternatively, and then say we can say feed is actually fed from this. Suppose the salt solution is supplied in the all the chambers, and then say cathode and anodes are actually we can say this one linked with this power supply like this cathode and anode, and then we can say this one whenever the charged materials are there, then as per their opposite charges the salts or we can say this one ions will be attracted towards the cathodes or anodes, and then we will be getting this demineralized product from the several different chambers of the electrodialyzer. Here also the same thing is drawn here, or we can say this one is shown here. Suppose raw wastewater actually is fed from this top with this distributor like this, it is coming like this in the different, suppose in alternate chambers, and then cathode and anodes are connected with this DC power supply, and then say as the raw wastewater contains some amount of charges. So, these opposite charges will be attracted towards, we can say, cathodic plates and anodic plates, and then whenever the product water actually will be coming out, that will be free from this all the charges. Okay. And then say effluent actually will be separated from the bottom of these alternate chambers. Okay. So, applications are like this: desalination of brackish water, then recovery of nickel salt from this electroplating rinse water, then demineralization of food like the removal of the salt from cheese whey, and so many electrodialysis applications are there. Then another process, that is we can say this pervaporation, that is nothing but the permeation followed by evaporation. So, pervaporation combines the selective permeation of one or more species in volatile liquid mixture and its some subsequent vaporization. Like we can say this one, this is the membrane. Suppose this is the membrane, and say we have this one hot feed, we will be discussing this one in detail. Suppose this feed is supplied, and then it is by the help of this, we can say this one condenser, this it is, we can say this one we can say it is made hot, or we can say it is heated, and then it is actually fed to this pervaporation chamber. And the opposite side of the membrane, say vacuum pump actually is there. So, that this whatever the hot feed enters, inside this hot feed, suppose few components are there which have this low volatility. So, at that condition, as the vacuum is created in the opposite side, then the we can say one or two components will be vaporized, and then this will enter through that membrane, and that will be collected through this vacuum pump. We can say this one condensed, whenever it will be condensed, then we can say this one condensed permeate will be collecting, or we can say this one whatever the more volatile components will be separated, and whatever the less volatile component will be retented. Okay. So, based on that we can say this one relative volatility, say this pervaporation is effective. And another point is that using this pervaporation, the very dilute solutions also are we can say this one treated, or we can say the whatever the solutes present in the dilute condition, these are also treated with the pervaporation. Application of pervaporation like this: preparation of absolute alcohol from this alcohol water mixture, we can say that is azeotropic dehydration of the solvent, then removal of organics from aqueous water solution at low concentration. So, this is we can say this one schematic of this system like this. We have this suppose we have this feed tank where feed is there, and using this gear pump we are putting this into the membrane cell. Suppose this is the membrane cell, and then suppose and say membrane, this is the membrane, and we are incorporating this feed here, and say vacuum is created in the opposite side of the membrane. So, then the high volatile material will be coming out from here, and whatever the more volatile component that will be retained there, then it will be collected from the other side of the membrane module. That is why we can say this one part is there what is called permeation cell. Suppose from here one part will be there which is we can say with this low volatility, or we can say which are with this very volatility, or we can say has this low boiling point. And here you see this vacuum pump is there, and say and cold trap also is there. Whenever it will be connected in this direction, then the components with high volatility, or we can say this low boiling materials will be coming through this one and will be collected in the cold trap. Okay. Whenever we will be discussing about the liquid membranes, I already told that these liquid membrane applications are not yet done industrially, or we can say this one due to its instability. So, the first type of this liquid membrane, that is emulsion liquid membrane, in brief it is ELM. The emulsion is essentially a double emulsion like water oil water or oil water oil system. Like for water oil water system, oil phase separating two aqueous phases, this one is the liquid membrane. Suppose this is the we can say this one water oil water globule, then this phase we can say this one oil phase will be separating two aqueous phases. Suppose here also aqueous phase will be there, then these two will be separated by this emulsion. For oil water oil system, water is the liquid membrane. So, means water will make the film. So, like bubble, water will make the film, and then surfactants are used for stabilizing the emulsion, and it actually creates the this liquid membrane. Like you say, we have this aqueous system and we have oil also, then we are adding some amount of the surfactant, then if we agitate this one, then we can say some amount of the, say we can say micelles will be formed like this one. So, this is one kind of, we can say this water in oil emulsion like this. And if we agitate more also, sometime if we agitate more, then it will be water in oil in water emulsion. So, in this we can say this one, in this inside this aqueous, again the bubble will be formed, and then this aqueous layer actually will be formed, and this suppose oil will be there inside this. So, there will be getting water in oil in water emulsion. So, that type of system also is there, or we are making some emulsion using this surfactant in presence of oil. Okay. That either this film of this oil or the film of water will act as the liquid membrane. And this one, the target component which will be separated using this liquid membrane, that will be entrapped inside this emulsion. Suppose we are trying to trap one say dye from this aqueous solution, then aqueous solution will be the feed, and inside this feed we will be generating this suppose water oil water emulsion, then oil will make one layer, and inside this water which is there, that will have some amount of, we can say the either sodium hydroxide or sulfuric acid or any other thing or gelatin compound which can make the complex with this dye. So, that dye will move through this we can say either oil barrier or water barrier to react with this whatever the component present inside this emulsion, or we can inside this globule, there it will be entering to trap, and this one to make the complex. Like this, the concentration of the this one, suppose this is one barrier, and outside this one suppose dye is present here, and here suppose sodium hydroxide is present. So, suppose this is oil barrier, this is say dye is in water, and say sodium hydroxide also in water. The concentration of dye will be here high, and inside this one it is 0. So, due to this concentration gradient, this dye will be entering through this emulsion, and then it will react with sodium hydroxide to this one to be trapped here, and say this one dye will be say separated from this aqueous solution to inside this emulsion. Once it will be bigger in size due to this entrapment of these dyes. So, these all the emulsions actually will fall down on this, we can say this one in the liquid emulsion system, and then these will be collected at the from the bottom of this container. But one point is that it has a limit, once it will exceed its limit, means then the emulsions actually will be broken, or so many emulsions will coalesce, and then the size will become larger, and sometimes these will also break. So, due to the reaction of some amount of reaction of sodium hydroxide with the oil also, we can say the stability of the this we can say film decreases. Okay. The second type of the liquid membrane, that is supported or immobilized liquid membrane. So, this is very simple. Suppose this is the actual membrane and inside this membrane so many big pores are there. So, it is made by impregnating a thin porous film of a suitable solid substance with the liquid. The porous film only supports the liquid within the pores. It does not have any role in the solute transport. Means suppose this is the supported liquid membrane. So, means this is the membrane and inside these big pores, suppose immobilized fluid phase or interface is there, and then when a particular target component is brought into contact with this membrane, then this material actually will be transporting through this immobilized phase, and then it will be separated in the another side of this membrane, that is we can say this one immobilized fluid phase interface 2, means from the opposite side of this supported liquid membrane. So, this is also used in the lab scale for the separation of so many dyes or so many metals. Okay. And then third type is this bulk liquid membrane. So, BLM is the simplest among these and is usually used in the laboratory for experiments actually. It is one U shaped cell where the membrane, we can say this one membrane is placed here and say in this at the bottom of this U tube, and the two aqueous phases are placed. Suppose one is this, we can say this one source phase, and in one arm of this U tube, and we can say this one another is this suppose receiving phase, and floating on the top of the organic membrane like this. So, here we can say this one in the contact of this, we can say this one organic membrane, say suppose the target component will be transported from here and then will be coming to this receiving phase. So, here also it is like this, suppose this is the receiving phase and this is the source phase like this. Here this organic membrane actually is placed, and then say we can say from the source phase this we can say this one target component will be coming to the receiving phase. Okay. For better transport of the solute getting separated, usually a magnetic stirrer is used. Suppose this is stirrer is used to make the better transport of the solute target component. Now, we will be describing the membrane characterization. So, whenever we will be demanding that or we will be claiming material as the membrane, then we have some guidelines or we can make this one in terms of some characterization parameters. The first parameter is membrane permeability, that the permeation ability of the membrane, or we can say this one whenever we have one target component, how much it can retain, or we can say this one whatever the carrier solvent or say solvent will be permeating through this one. So, membrane permeability of a porous membrane can be determined by measuring pure water permeate flux through this membrane at a given pressure. So, flux values at various operating pressures are measured, and the slope of the flux versus pressure plot gives the permeability. So, we will be as per the Darcy's law actually will be say as by the Darcy's law we can say JW, that is we can say water flux is proportional to, we can say this one driving force del P minus del pi. Okay. So, this is actually we can say this one volumetric flux. Whatever the permeate actually will be coming out through this membrane, that is we can say this one pressure gradient, this is osmotic pressure. So, we can say this one pressure gradient, this is osmotic pressure. Okay. So, JW actually we can say this one JW is equal to, so one constant parameter is there, proportionality constant, that is LP del P minus del pi. Okay. So, this LP is called this membrane permeability. So, this LP is nothing but we can say this proportionality constant of flux versus driving force. Okay. So, this is called this permeability, membrane hydraulic permeability. this membrane hydraulic permeability. So, if we plot say del P versus JW, so we will find that this is suppose 0 0. So, if we increase this as per this Darcy's law, if we increase the driving force so on the membrane system, then permeate flux value will go on increasing, because this is linearly proportional. So, we can say this one, if we increase this driving force, then we can say flux value will go on increasing. Okay. And this slope actually is will give LP. Okay. So, LP is nothing but we can say this flux value is we can say meter cube per meter square second, and then pressure will be suppose this Pascal or kilopascal. So, the unit of LP will be meter cube per meter square second into Pascal. Okay. Or simply we can say this one meter per Pascal second. Per Pascal. So, it will be like this meter per Pascal into second. So, unit will be the unit of LP will be meter per Pascal second. Okay. And say this one, the membrane permeability actually this tells us about the we can say the how porous the membrane is. If we say this high LP means then we can say this one this membrane is highly porous. If we say this very low LP, then we can say this one the membrane is less porous. So, this is we can say this one highly porous. If we say low LP, then it is very less porous membrane. So, we can say this one the microfiltration membrane has maximum porosity, whereas we can say this one reverse osmosis membrane has less porosity. Okay. And also this one this LP, that is we can say this one is equal to JW, that is permeate flux by del P minus del pi. So, we can say this one minus del pi, but for pure water say del pi will be 0, that is we can say this one will be JW by del P. So, that is actually we can say will be equal to 1 by say mu into Rm. So, LP is equal to 1 by mu into Rm. Okay. So, where this mu is this we can say this viscosity and Rm is the membrane resistance. So, that mu is equal to we can say this one is the viscosity, mu is viscosity of the permeating solvent, and Rm is membrane permeability. This is we can say membrane resistance, Okay. So, that we can get this one if we know the resistance of the membrane itself, because you see membrane is the porous medium, it will offer some resistance, and if we know the viscosity of the we can say permeating this one what is called fluid, then LP also we can get from here. Okay. And we know that osmotic pressure delta pi, that is equal to say we can say IRTC by m. So, in case of this high molecular weight compounds, the osmotic pressure is very less, and whenever we have this low molecular weight compounds and ionic species, their osmotic pressure value is very high. Okay. Then next characterization is by observed retention. So, this how much solute concentration in the permeate stream compared to the feed stream is quantified by this observed retention. Okay. So, observed retention actually we can say this one RO is equal to we can say this one 1 minus C0 by Cp, sorry Cp by C0. So, this we can say this one observed retention is equal to 1 minus Cp by C0, means if we have this membrane, suppose we have this membrane and solute concentration in the feed side is C0 and permeate concentration means the concentration of the solute in the permeate side is Cp, then how much actually is retained, means the solute concentration will be retained, that is we can see this one 1 minus Cp by C0, that will give this observed retention, means that amount of is retained by this membrane. Okay. So, that is we can say this one observed retention. And Cp is we can say this solute concentration in permeate, and C0 is solute concentration in feed. Okay. And then next characterization is real retention, but we know that this membrane separation process is a dynamic process and it is not governed by the equilibrium of the system. It indicates that whenever the permeation operation is on, then the solute concentration on the feed side will go on increasing. Okay. So, in the beginning the solute concentration was C0, but whenever the process will be completed, that time the solute concentration will be much more higher than C0, because the solvent has passed through the membrane, keeping the solutes in the feed side. So, we can say this one, it is actually we can say the membrane solute solvent interaction parameter. So, this defines the selectivity of the membrane, or we can see the property of the membrane solvent solute system. There RR is equal to, we can see this one observed retention is equal to 1 minus Cp by Cm, where we can see this one Cm, say here actually you see Cm is equal to membrane surface concentration, means it is the maximum concentration of the solute on the membrane surface. So, suppose in the beginning the concentration was C0, but say when the process is completed, that time the solute concentration is increased from C0 to Cm, but the Cp actually is we can say the permeate concentration. So, now from here we can this one get that this in case of this observed retention, that is we explained as 1 minus Cp by C0, and Cm of the real retention is equal to, we can say this one 1 minus Cp by Cm, and we know that Cm is much greater than C0. So, from here we can say that real retention value, we can say this is much will be at least greater than say observed retention, as we can say the Cm is greater than 1. So, we can say this one right hand side in the this one second term of this right hand side will become say lower, that is why it will be say RR will be high. But we see we can get the this one we can estimate this observed retention real retention value. The velocity gradient method is there. We need to take a star vessel, then with high speed there, whatever the we will be getting this observed retention, then that will be this real retention, because membrane surface concentration is a fictitious concentration. We cannot measure this one instantly for a particular membrane operation, because it is completely dependent on the operating condition. Okay. So, but it is initial concentration and whatever the permeate concentration that we are getting, this one we can get from the experiment. Okay. And then another characteristic is this molecular weight cutoff, that is MWCO. That is MWCO is the molecular weight of a globular protein or any other standard monodisperse solute like dextran, PVP, etc., 90% of which is rejected by the membrane. Like this we can say, if we draw one, we can say this one observed retention RO with say log of molecular weight cutoff. Molecular weight actually, log of molecular weight actually, if we plot this one, say if we plot this log of molecular weight and RO, then we will be getting, suppose one graph actually we will be getting like this. Whenever this 90% 0.9 actually we will be getting here, then a corresponding molecular weight. So, we will be getting this log of molecular weight. From there whatever the molecular weight we will be getting, that will be MWCO. Okay. And semi-log plot of the molecular weight and observed retention gives this S-shaped curve like this one. The straight line of the curve correspond to MWC of the straight line of the curve. We can say this in general, we can say this one, if we have this sharp molecular cutoff like this, suppose if this is the we can say this one observed retention versus log of we can say this molecular weight, then say this one, this will correspond to MWCO. So, this is we say this sharp MWCO, but you see this one sharp MWCO generation or manufacturing is very tough, but in reality most of the membranes are with diffused molecular weight cutoff like this. So, where we can say this one, the there is no straight part actually in the RO versus log MW part, that is we can say this one diffused molecular weight cutoff. So, in this case, in case of this diffused molecular weight cutoff membrane, so there will be a distribution of the we can say this one we can say the permeate concentration for the entire experimentation, or we can say the Cp value will be varying actually, or we can say this one will be getting range of these Cp values for the we can say particular membrane operation. Okay. And another characterization is this we can say porometry. So, all pores of a membrane may not allow permeation of the solvent actually. So, maybe some of the pores may be dead, or maybe say we can say this one suppose this is the membrane, and then suppose the shape of the pore is like this, or sometimes say suppose this pore has bifurcated, or maybe this part is damaged, suppose this part is now dead. So, maybe so many combinations may be there. So, porometry is useful and convenient technique for the determination of the size distribution of active pores in a membrane in the size range of 10 to 100 nanometer. So, in this range actually we can say pore size we can distribution we can get. Now, this basic forms of the transport. Say one is this facilitated transport, that is carrier mediated transport, another one is coupled transport, and third one is this active and passive transport through this membrane. So, first one is this we can say this one facilitated or carrier mediated transport. This is very simple, it is a process of movement of species A with reactive agent C, that is called the carrier. Suppose A and A is there, so this is our target component, that will be separated using this membrane, and one carrier component is there, that is we can say this is C. So, now it will be making one complex like Ca. Okay. The carrier is a mobile species that reversibly reacts with A at feed side to form permeate carrier complex Ca. So, it will be moving from one side of this membrane to the other side, and then in the other side actually C will free A, then it will be obtaining this one. Okay. Okay. This Ca diffuses through membrane, reaches the permeate side and releases the permeated A. So, here actually A will be separated like this. The concentration of the A is shown here through this Z, means that through across this thickness. Suppose this Ca is there, because C is the carrier, then Ca concentration will go on decreasing across this membrane, and then here actually we will be getting the A, where this, in other words, this concentration of solute actually C will be increasing in this direction. One example of this transport of the oxygen through the lungs membrane is an important example of the facilitated transport of oxygen. Like the oxygen is entering in the you will be transported through this hemoglobin, and then in the lungs actually oxygen will be, we can say, separated, will be, we can say, this one discharged, and then hemoglobin again will be coming back to the water system. And then second one is this coupled transport. The coupled transport has some similarities with the facilitated transport, except that complex BC forms on the downstream surface of the membrane by reaction with the species present in the permeate site liquid. This species diffuses through the membrane, reaches the upstream surface and reacts with A and releases C like this. So, this is almost similar to that of the facilitated transport, only here you see this one, say suppose A is there, it will this one coupled with BC, and then suppose and AC will be this one will be transporting from one side to the another side, and there it will be this one reacting, this will be say in the permeating side, this say B will be freed, and then it will again react with C to make BC, it will be coming back and releasing this A. Like that way, say A is transported from feed side to the permeate side, and B this one from permeate to feed side like this. So, the phenomena is called coupled transport. And the last this one for basic form of transport, that is we can say this one coupled this this example of this coupled transport is recovery of copper from this waste liquor using this microporous membrane impregnated with solution of say LiX64N containing an oxime dissolved in organic medium immiscible with water. The oxime forms a complex salt of copper 2 plus at pH we can say this at pH 2.5, and the complex diffuses through liquid pores of membrane solution on that side has a lower pH of around 1. So, at this pH this complex reacts with H plus forming protonated oxime Bc and releasing Cu2 plus. Like this will be like this. Suppose this is the membrane, and then suppose this is the feed side. So, pH is 2.5 and this is the permeate side. So, pH is 1. So, copper 2 plus is there and oxime also is there, and say it will be transporting like this one, say copper 2 plus oxime complex, and then say here actually copper 2 will be separated, and then only oxime will be coming with H plus. Okay. So, that is we can say this one. So, here we can say this in the feed side copper 2 plus and oxime H plus will be there, will be converting into copper 2 plus into oxime plus H plus. In the permeate side copper 2 plus and oxime plus H plus actually will be giving oxime and H plus and releasing Cu2 plus. Okay. Third and last form of transport is active and passive transport. So, in active transport process it generally works against a concentration gradient like pumping molecules from a lower concentration on one side of the membrane to the higher concentration at the other side. So, active transport is an important phenomena in biological systems like movement of sodium plus and potassium plus ions through the cell. Say suppose this is the membrane. So, through this we can say this one A is moving from low concentration to this high concentration zone. So, that is actually we can say this one active transport, like say sodium plus and potassium plus ions through the cell membrane of this red blood corpuscles against concentration gradient, and other type of transport like this of glucose into the liver cells means from the lower concentration to the higher concentration. So, but in case of this passive transport it does not require any form of we can say metabolic energy from the cell. It is, we can say this one, it can move from higher concentration to lower concentration due to the chemical potential gradient like this. So, that will be the function of, we can see the temperature, pressure, concentration, electrochemical potential, like this is actually we can say just like simple diffusion process. So, this is, we can say this, in other words we can say this is passive transport. Okay. Like say feed has this chemical potential of mu a, due to this chemical potential value low in the, we can say this in the permeate side, or we can say this one in the strip side. So, a particular target component A will diffuse due to this passive transport, or we can say this is one just by simple molecular diffusion. Okay. So, now we will be discussing about the membrane module. So, there are so many different types of modules available for this industrial application, for the academic research also, in the lab scale, in the pilot scale, or in the we can say this on industrial scales also. The first type of simple module is plate and frame filter, that is we can say plate and frame membrane module. Then we have star cylindrical cell module, then third one is tubular module, and fourth one is hollow fiber membrane module, fifth one is spiral wound membrane module, then sixth one is rotating disc membrane module, and seventh one is spinning basket membrane module. So, other membrane modules also are available, which are, we can say this one pilot scale as well as this industrial scales also. We will be discussing briefly all these membrane modules. Like for plate and frame membrane module, this is very simple. So, we can see it consist of number of plates and each plate having a frame around its perimeter, and say all the plates and frames are like we can say stacked one by one like this, and in between plate and frame this membrane will be placed. Suppose membrane is placed here. In general, what is happening over this frame, the membranes are placed. So, if we place the membrane in the two sides of the plate, then another frame actually will come, and then we can say whenever this suppose feed will be entering, then feed will be leaving entering actually in all the, we can say this one frames, and through frames this feed will enter, and from the we can say suppose in some cases the sunrise type grooves are there. Through this groove, the suppose through this, and from the corner of this we can say the plate, the permeate will be collecting, and then it will be collected in a common header, and it will be taken out from this plate and frame membrane module. It is simply we can say plate and frame filter type. Advantage is that these sheets can be kept quite close, and these can be taken apart for cleaning and maintenance. Just if we open these plate and frames, the frames from all the plates, then we can reuse this plate and frame membrane module very easily, and if it is we can say choked also, we can clean this very easily, and that is why you can see this one maintenance of plate and frame type membrane module is very easy. And then second type is the star cylindrical cell module, like this is a cylindrical cell, and say this is a batch cell. So, in the beginning we need to feed this feed inside this membrane module up to a certain height, then we need to pressurize the system as per requirement of the membrane system. If it is a microfiltration, the low pressure is required. If it is a reverse osmosis, then high pressure is required. And then so this above this membrane, suppose this is the membrane material, then above this membrane suppose one stirrer is there. This stirrer may be we can say this magnetic stirrer, it may be mechanical stirrer, whatever this one arrangement is there, it is fine with the system. So, to reduce this concentration polarization, we will be discussing about this concentration polarization in detail at the end of this lecture. So, something will be deposited on this one, that solute will be deposited as this solvent will be coming out from the system. So, we can say this permeate or filtrate is devoid of the solute. So, we can say solute concentration will go on increasing on the membrane surface. To reduce this concentration polarization, say stirrer bar, or sometimes we can say this one using this mechanical stirrer, we can say that can be stirred. So, that say the solute concentration at the membrane surface will decrease, and then we can say the efficiency of the membrane filtration process will go on increasing with time. Okay. Then third type is tubular module. So, it is simply we can say this one like cell and tube heat exchanger. So, all these we can say tubes are placed inside one chamber like this, and then feed is entering from this, we can say this from one side of this we can say tubular system, and the feed will be now distributed among all the tubes, and from the tube side the permeate will be collected, and then will that will be taken out from the system. But the concentrated residue, or we can say this one retentate, will move through these pipes, or we can say tubes, and will be collected from the opposite side of this we can say this bundle, and then it will be taken as the this concentrate or retentate or reject. So, there are so many advantages of these tubular modules like this. These can be operated with simple pretreatment of the feed, and these can be mechanically cleaned just by we can say this one opening the tube seats from the we can tubes from the tube seats, and we can clean this one using this brass or like this, and then again we can place this one inside this we can say the cell, and membrane area or module space is small, and membrane contamination is minimized by high feed flow rate, because that time the solute deposition may be minimized inside this tubes in the tubular membrane module. Then fourth type is hollow fiber membrane module. This is we can say this one another form of the tubular membranes, but it consists of very narrow tubular this one entrance with outer diameter ranging from 25 to 250 micron, and wall thickness of 10 to 50 micron of the we can say this narrow the fibers. The main disadvantage is its sensitivity for fouling, since there is a little space in between the fibers. So, we can say this one the tubular module and hollow fiber modules both are almost same, and operation wise we can say this one also same, only the difference is that in case of tubular modules we have these big tubes, but in case of these hollow fiber modules the all the fibers are with very this one low inner diameter as well as this outer diameter. And there are so many applications, mostly the hollow fiber membrane modules or cartridges are used in hemodialysis, and then artificial kidney, then blood oxygenator, then we can say this one dispersion free liquid extraction, then we can see this deoxygenation of the boiler feed water, and so many other applications. But main disadvantage of this cell is that these we can say the fibers are contaminated very easily, because the clearance between these two fibers are very less, and once this small particle is also sticked inside this one, it is very much this one impossible to clean this as the inner diameter of the fiber is very less. That is why these are prone to choking, and then we can say efficiency of the membrane cartridge will decrease very drastically. Then fifth type of this module is the spiral wound membrane module. This is widely used in the so many industrial applications. So, this module consists of large and membrane envelope loosely rolled like a sandwich. So, in between say two membranes, suppose one spacer actually is used. Spacer is nothing but the we can say grate type of material made of these metals, and this grate or we can say this one spacer gives the entry point to the feed. So, suppose if we have two mills like two seats are available, then in between two membrane seats one spacer is placed, and then it is rolled and it is kept inside one say cartridge, and feed is entering, say we can say this one from one side of this we can say the system, and then say feed will be we can say this one distributed among all the we can say suppose feed is entering from any side, and then say whenever suppose feed flow is in this direction, and in all the we can say open channels feed will be distributed, and permeate will be collecting through the spacer in a common header, and that will be collected in the perforated say permeate collection pipe, which where the we can say these membranes are housed. Okay. And residue will be collected from the other side of this we can say this wound, and there from the common header the residue or we can say the retented or reject will be collected. The main beauty of this spiral wound membrane module is that it is in a small space we are able to provide huge surface area. We will say for 1 meter square membrane surface area we need only a small we can say only 1.5 feet long we can say this tube with only we can say 3 to 4 inch diameter this tube sheet is sufficient to keep 1 meter square area, and it can withstand up to high pressure like more than 1000 psi pressure also. This is compact and high membrane packing density. So, we can see the efficient utilization of the floor space and minimum concentration polarization and low membrane contamination, and this is very easily we can say clean this spiral wound membrane module. The another one is this rotating disc membrane module. So, one say disc actually is placed with the shaft of this one we can say with this of the driving motor, and then the suppose this feed is entering from this from one side of this we can say chamber, like this is the chamber, and then say in case of this highly concentrated this feed we can use this rotating disc, and then membrane is placed here, and through this membrane say permeate will be collecting, and then it will be collected from one particular point, and retented will be collected from this we can say from one common header type thing, and say whenever the solute will be deposited on the membrane surface, due to this rotation of the we can say disc, the concentration polarization or deposition of the solute will decrease. I told that this is mostly efficiently used for this highly concentrated feed, or we can say this highly viscous feed. Okay. And so, this is we can say the single rotating disc. We have this multiple rotating disc, that is called dyno rotating disc. Suppose the retented is coming from one rotating disc membrane module. If it is fed in the next one like this, if it is fed in this like in the next one, so then here also again we will be getting retented and permeate also. So, whatever permeate actually we will be collecting, every permeate will be collecting for so many rotating disc systems, and then one common through this common header we will be collecting the permeate, and whatever the retented will be getting from the say we can say consecutive steps, or we can say these systems, these will be collected in a common header, then retented will be collected from a one common outlet. Okay. And the last one is this we can say the spinning basket membrane module. This is we can say this membrane module is the recent development of the membrane modules. So, here the disc itself is rotating, and the suppose the we can say this agitator contains the membranes. Suppose this agitator has 4 blades. So, in 4 blades these are our hollow agitators, this one all these are connected with this one common header, we can say this one permeate collection line, and so this in all the agitator blades in one place the membrane is placed. Suppose the opposite side of this blade the membrane is placed like that in this side. So, in one side of the agitator blade membrane is placed. So, we have 4 membranes in 4 different blades in the same orientation, and the common header is like this is the rotor of the agitator, and say whenever we will be placing this one say we can say this one tank like thing over this we can say this membrane module, then through there actually we will be putting the retentate line, and say feed actually is entering from the bottom of this system, like this is the feed line. So, feed is coming and then it is entering through this hole, and initially it will fill. In case of the slurry materials, it is observed that after some times the slurry will become very concentrated and it will try to be deposited over this we can see this tank, but in this case the membrane is not placed at the bottom. So, this membrane will not be choked, but membranes are all placed vertically on the agitator blade. So, it will whenever it will be rotating, then it will this one due to the centrifugal force, the solvent will be entering through this membrane and it will be collected in a common header, and then we will be getting the permeate. So, whenever we will be working with slurry type material with high concentration, this spinning basket membrane module actually is very much effective. Like this is the spinning basket membrane module. From the feed tank it is entering from the bottom and permeate collecting from the common header, and retentate will be again recycled back to this feed, or whenever we require this we can take out this retentate from the we can say this one outlet of this tank like this. So, that is why from this basket, from the top of this basket we will be able to collect the retentate or highly concentrated slurry, and from the bottom we will be able to collect the this fine we can say this one pure permeate, or we can say this one permeate without the slurry materials. Thank you. So, in the next class we will be discussing about this manufacturing of the membranes, then advantages of the membrane separation processes and limitations and approaches to improve.